Now another sufficient condition is when the function may not be continuous, but it can be broken into finitely many pieces where it is continuous. So this is the definition of a piecewise continuous function. So a function, let's call it f, from a closed interval a b to r is called piecewise continuous if there exists a finite subdivision, of this interval a b into finitely many subintervals such that on each such piece, on each such subinterval, the function f is continuous and at each endpoint of this of all subintervals, so at each endpoint of each subinterval, the left hand limit and the right hand limit exist. Right hand limit exist, but they may not be equal. So we have already seen an example, so let me redraw. So this is our A, this is our B. So if we can divide this interval AB into finitely many pieces, like this, so each such subinterval is a part of the subdivision. Now our graph of this function f, which is now a piecewise continuous function, will look like something like this. So this is so on each piece it is a continuous function and the left hand side and the right hand side limit exist, which mean that they are finite limits. So here the first chunk looks like this, but the second chunk may look like this, the third chunk may look like this, the fourth chunk may look like this, and so on. Okay. So this is on each subdivision, it is a continuous function, and when you approach at any endpoint, let's say this one, at any endpoint, if you approach it from the left and you approach it from the right, the limits exist, but they may not be equal. In case of a continuous function, they were equal, and they were equal also, the left and the right hand side limits were also equal to the value of the function at this endpoint, but here also they may not be equal. So first of all, the left hand and the right side, the right hand limits may not be equal, and they may not be equal to the value of the function at this point, which may lie here. So this is, if this point is C, this is can be f of C, and this is the left limit and this is the right limit, and all three are different. Still the left hand and the right hand side limits exist, and this is all we want for a piecewise continuous function. So what is not allowed here is if you want to have, say, if I delete this first chunk here, now let's say it starts here, but at this end point it goes to plus infinity as an asymptote. Okay, it has an asymptotic value plus infinity at this end point. So this kind of behavior is not allowed. So similarly, you cannot have minus infinity as a vertical asymptote going to minus infinity at this end point or at any end points like this. So this kind of behavior is not allowed. Once we know the definition of piecewise continuous function, we can state a sufficient condition that integral a to b ft dt exists if f is piecewise continuous on this interval ab. Okay, so this gives us sufficient conditions for the existence of Riemann integrals on closed and bounded intervals. Now for improper Riemann integrals, we can state a sufficient condition, improper Riemann integrals of the form integral a to infinity ft dt. So we can state this theorem, which is a sufficient condition for existence of this integral. So we can write that integral a to infinity ft dt exists if, first condition, the function ft is piecewise, the function ft is piecewise continuous on the interval a capital R for all r greater than a. Okay, first of all, it has to be piecewise continuous on this closed interval AR for every r greater than a. Secondly, we suppose that ft is greater than or equal to 0 on a infinity, on this region a infinity. So we suppose that the integral is positive, the function is positive. And thirdly, we suppose that integral a to r ft dt is bounded above by some constant m for every r, for some m for every r greater than a. Okay, so if these three conditions are met, then we say that, then we can rest assured that our improper integral a to infinity ft dt will exist. Okay, so this is one sufficient condition. Another sufficient condition is given as follows. So assume 1 and 2 in the above theorem. Meaning that, first, that ft is piecewise continuous on each interval of the form AR, closed interval for r greater than a, and it is positive on a infinity. Now we suppose that there exists a function gt such that ft less than or equal to gt for all t in a infinity, So ft is bounded above by this function gt for all t, and the improper integral gt dt exists, then we can say that the improper integral of ft dt also exists. So this is a kind of comparison theorem where you have two functions, and the right hand side function you know that its improper Riemann integral exists, then the improper Riemann integral of the left hand function is also finite and exists. So these are two sufficient conditions that I want you to know, and they can be used to check whether some integrals are exist as an improper Riemann integral or not. So let me give a couple of examples. So the first case is ft is e to the power minus t. Now we already know that this integral, the improper Riemann integral from 0 to infinity ft dt exists. We have computed it using the limits, but we can also apply the first theorem as follows. So what we need to prove that is that integral 0 to r e to the minus t dt is bounded above by some m for all r greater than 0. So this is what we want. So let's see if this is true. What is this integral? We can evaluate it directly, and we find that this is 1 minus exponential minus r. So of course it is easy to see that this is always less than or equal to 1 for all r greater than or equal to 0. So therefore we have found this upper bound m, which is equal to 1 in this case, and therefore we can say that this improper Riemann integral exists. Another example is as follows: ft equal e to the power minus t squared, okay, 1 less than or equal to t less than infinity. So let us see whether this integral 1 to infinity ft dt exists or not. So this is equal to limit r tends to infinity 1 to r e to the power minus t square dt. This is the definition of the improper Riemann integral. Now note that in the first example, e to the power minus t, we can evaluate this integral explicitly, and we can answer the question using the first theorem. But here we don't know how to evaluate it explicitly, so we will use the second theorem here. So note that for t greater than or equal to 1, t square is greater than or equal to t, right? Therefore e to the power t square is greater than or equal to e to the power t, and this implies that e to the power minus t is greater than or equal to e to the power minus t square for all t greater than or equal to 1. Now we can apply the second theorem. The second theorem with gt equal e to the power minus t. We know that integral 1 to infinity e to the power minus t dt exists. Okay. In the same fashion as we did it for 0 to infinity, we can also evaluate it from 1 to infinity, and one can show that this exists. And we have shown that this is e to the power minus t square is less than or equal to e to the power minus t, and these are both positive. Therefore by the second theorem, integral 1 to infinity e to the power minus t square dt also exists.